Thank you very much for the introduction, and thank you to Serge for the invitation, and thank you to the local organizers for the great organization of this workshop. It's a great pleasure and honor to present our results here. It's my first time to Hong Kong, and it was really a very exciting time already. So the title of the talk is Chiral Quantum Optics, and I would like to start with a short disclaimer. Actually, in the context of this talk, the word chiral here probably means something very different from what your favorite usage of the word chiral might mean. So in the context of this talk, chiral refers to direct propagation, direction dependent. So here we're talking about a propagation, direction dependent interaction between light and matter. And we will see how this comes along and what it has to do with the confinement of the light fields that are involved. So maybe to give a broader context of our work, it's actually in the framework of so-called hybrid quantum systems, and the idea of a hybrid quantum system is the same as for a classical quantum system. You want to combine the good properties of two systems, like here a combustion engine and an electric motor, to achieve something that is not easily achievable with each of the subsystems. And in our work, what we combine are actually atoms and photons. So the reason is that photons have very advantageous properties when it comes to transmitting information, because they propagate at the speed of light, and they are very easily detected, and their state, when it comes to their polarization, for example, is easily manipulated. And they are very weakly coupled to the environment, meaning that it's really ideal to send information and also quantum information from A to B. Atoms, on the other hand, are wonderful quantum systems, above all because they are identical, okay? And they are also very inexpensive, if you think about it. So you get 10 to the 21 rubidium atoms for $1. I stole this joke from Jean-Michel. And they have a well-known level structure and optical transitions, meaning that you can control both their internal and external degrees of freedom using laser light. The excellent ground state coherence properties have been exploited for atomic clocks, but also mean that you can store quantum information in these ground states. And one could say that a single atom is actually the most non-linear thing you can think of, because a single atom reacts differently to two photons than to one photon. So this means that atoms are ideal for storing and processing, when it comes to the nonlinearity, quantum information. So the task we have to tackle if we want to combine these two systems is to realize a quantum interface between such atoms and here I stress, propagating optical photons. So it's in general not enough to have the photons confined in a box, because eventually you would like to send this photon from one point A to another point B in order to communicate also. And actually, this is challenging for the simple reason that the interaction cross-section between atoms and photons is very small. So in order to have a high enough probability for a given photon to interact with a given atom, you have to focus the light very strongly, such that the cross-section of the light field is comparable to the interaction cross-section of that atom. And that can be done in free space by strong focusing, but it can also be done, and has been done, using optical components, optical waveguides. So for example, by inserting laser-cooled atoms into hollow core fibers, by inserting atoms into waveguides with a gap between two end faces of the two ends of the waveguide, by inserting atoms from the side into the evanescent field surrounding a waveguide, in this case a one-dimensional photonic crystal cavity, or by combining, in a sense, these two approaches here and having a photonic crystal waveguide with a slot in it, and the idea is to put the atom where the high field intensities are. And the main message of this talk now is that actually one should consult Maxwell's equations before doing experiments or applications where you couple emitters to light fields if the light fields are transversely confined at the wavelength scale. Okay? And in order to understand the physical reason for this disclaimer here, we have to understand the polarization properties of such confined light fields, and actually you can immediately understand them and also everything about the physics if you just understand water waves. Okay? So if you consider a water wave traveling along the surface of the water, then the speed of sound at the surface here is much smaller than in the bulk. So that means that the amplitude goes down and the water is basically standing still a few wavelengths below the surface. Okay? But then, given the fact that the amplitude diminishes with distance from the water surface, if we now take the continuity equation for the water, which involves an incompressible fluid where mass is conserved, then you cannot have a transverse oscillation of the water here without having a longitudinal component at the same time, meaning that the water flows actually in more or less circular orbits here. So the flow of water, due to this divergence of the velocity field that has to vanish, must go in circles. But that also means that the sense of this circulation will now be correlated to the direction of propagation. Okay, so here you see that the flow is clockwise, but if I now reverse the direction of propagation of the wave, then the circulation will be counterclockwise. So there's a one-to-one link between the sense of circulation and the direction of propagation. And what we will see is that you can make use of this effect in the context of light waves, so surface waves of light, in order to realize what we would call chiral coupling, so direction-dependent propagation, direction-dependent coupling of light and matter. So if you put an emitter in such a light field, say in the evanescent field surrounding a dielectric waveguide, then in addition to the standard, let's say standard situation, where you have symmetric coupling, so where the emitter sends as much light to the left as to the right, we are able to realize chiral coupling, so where the emitter sends more or even all of its light that is coupled into the waveguide to one side of the waveguide. And we can control the sense of this emission and tell the emitter, and now send your light to the other direction. Okay? And this is a surprising situation if you think about it, because we are talking about a translation invariant waveguide and a point-like dipolar emitter, and still something breaks the seemingly there's a mirror symmetry here, right? And something breaks that symmetry and makes the light go to the right rather than to the left. Okay? So with this, I come to the overview of the talk. I will first present our experimental platform, which are optical nanofibers. Optical nanofibers are cylindrical dielectric waveguides with a diameter smaller than the wavelength of the guided light. And I will then show you that by coupling emitters to such nanofibers, to the evanescent field surrounding nanofibers, you can realize a direction-dependent coupling and emission into the waveguide, both with classical emitters, so these are plasmonic particles, gold nanoparticles, and with laser-cooled atoms. And then I will come to some useful application of the physics involved in this by presenting some non-reciprocal nanophotonic devices, where non-reciprocal means that these devices treat light differently if it propagates from left to right or from right to left through the waveguide. Okay? So our nanofibers are realized as the waste of tapered optical fibers. So these are standard step index optical fibers, which we flame heat and pull in a very controlled way. And we reduce the outer diameter, which for the standard fiber is 125 microns, to a diameter on the order of half a micron or even less here. And in this taper transition, what happens is that the mode which is guided by the core of the standard step index fiber here is adiabatically transformed into a mode which is guided by this new step index fiber, if you like, because here the cladding becomes the new core and the surrounding air or vacuum is now the cladding. Okay, so this is again a step index fiber, and you can mode match perfectly this mode to this cladding guided mode and back into the fundamental mode of our fiber with better than 99% transmission. So this is quite a impressive number. It goes up to demonstrated values of 99.95% at JQI in Maryland now. Is quite impressive if you think about what brutal things are being done to the light field. You squeeze a few micron diameter light field into this 300 nanometer thin wire, and it comes out again with basically no losses. Okay. So if you now consider the intensity distribution of the mode, of this nanofiber guided mode, then you see that actually a large fraction of the optical power is present outside of the waveguide in the form of an evanescent wave. So typically about 50% of the optical power propagates in the form of an evanescent wave outside of the fiber. You also see that the cylindrical symmetry of the waveguide is not reflected by the intensity profile of the mode. This is because the light field that is guided in this fiber is now considered to be quasi-linearly polarized, and this linear polarization breaks the azimuthal symmetry. You can see that by considering that here it's guided by total internal reflection, which is here P polarized, because if this is my fiber, then the field is reflected like this, whereas here it's S polarized because the light is reflected like this on the fiber surface. Fresnel coefficients are different for S and P polarized incidence, and so you get a factor of 3 modulation of the intensity. And now here we have, again, as for the water wave, such a very strong gradient of the amplitude, okay, in the direction of the transverse oscillation of the, in this case, however, it's not the velocity of the flow, but it is the electric field. However, the electric field follows exactly the same equation as the flow for an incompressible fluid. The divergence of the electric field outside of the fiber has to vanish. So that means that as for the water wave that we saw, the electric field vector, if I send linearly polarized light into such a nanofiber, will turn, the tip of the electric field vector will trace a more or less circular orbit, okay, which in this case turns counterclockwise above the fiber, and for symmetry reasons it will turn clockwise below the fiber. Now you can attribute to such a circular polarization also a quantity which is called spin. In this case, spin is a classical electrodynamic quantity which represents the internal angular momentum carried by the light field, and it turns out that the spin in this case is transverse to the direction of propagation. So one talks about transverse spin of light in this context. And this transverse spin of light now has important consequences when it comes to reversing the direction of propagation, because as for the water wave, if I now send the light rather than from the left, from the right into this fiber here, then the electric field vector will turn clockwise. So the spin, the transverse component of the spin, flips sign when the direction of propagation changes. And this effect is so that the local ellipticity of the light field, or the spin, changes sign with the direction of propagation, is referred to as spin momentum locking of light. Okay, this means that if this is the direction of propagation and the spin points in this direction, if I reverse the direction of propagation, then the spin has to flip. Okay, so there's a one-to-one linking between direction of propagation and local spin. Now, this allows us now to break this symmetry of dipolar emission that I was referring to. So let's just explain what I mean. If you consider a dipolar emitter in free space, be it linearly polarized along the quantization axis or be it circularly polarized in the plane normal to the quantization axis, in both cases the emission pattern of the dipole exhibits two symmetries. First of all, there's a cylindrical symmetry with respect to the quantization axis, and there's a mirror symmetry with respect to z equals 0. And these two symmetries taken together imply that the emission in any given direction of space will always be the same as the emission in the opposite direction. Okay? However, if we now have such a dipolar emitter coupled to a light field that exhibits spin momentum locking, then we can break the symmetry and realize a directional dipolar emission. And the recipe is simple. We just have to locate the emitter on one side of the nanofiber. We have to suitably excite it in such a way that it now emits a, say, sigma plus polarized photon, where sigma plus means circularly polarized with respect to a quantization axis that points out of the board here, okay? And now the only optical mode that is guided in the nanofiber that exhibits such a circular polarization in the plane of the screen is a mode that propagates upwards, okay? So that means that the emission will exit the fiber on one side rather than the other. So we can realize the situation. The first experiment we did was with a plasmonic emitter, a gold nanoparticle that we deposited on the silica nanofiber and that we illuminated with a resonant light field, so it's indeed green in that case, which was initially horizontally polarized, where horizontal means the polarization coincides with the direction of the fiber axis. But then we send it through a quarter wave plate, and this angle theta here, by tuning this angle, we can set the polarization from linear to sigma plus or to sigma minus at will. And then what we record is the flux of photons coupled into the nanofiber and which exits our fiber. And we detect this flux with two photon counting modules, which I just call left and right detector in the following. And I can now define a quantity which you would refer to as directionality, which is simply the difference between the count rates between the left and right detector normalized to the sum of the two count rates. And if I plot this directionality as a function of this wave plate angle here, then I expect a large modulation. Actually, this quantity can, in theory, go from +1, where all the light arrives on the right detector, to -1, where all the light arrives on the left detector. So here I plot this directionality as a function of wave plate angle. So 0 means that I have linear polarization at the position of the emitter. If I go to 45 degrees, then behind the wave plate the light is circularly polarized. It's still slightly distorted because it also interacts with the nanofiber. However, I see here, the dots are experimental measurement, that I indeed have a strong modulation that goes from large positive to large negative values, where the left and right detectors interchange roles if I go from left circular to right circular polarization. Okay, so this measurement, so the solid line here is a theoretical fit to the data that takes into account the local polarization of the light field that impinges on the nanoparticle. And I should stress that the nanoparticle is spherical, so it will just replicate, its dipole will just replicate the polarization of the incident light field. Okay, so here for modeling the data, I take into account the polarization of the light field that drives the nanoparticle and the local polarization properties of the nanofiber guided modes, and I just compute the overlap between the two. Okay, and now this was done for the nanoparticle more or less on top of the nanofiber, this measurement here. If we now put the nanoparticle below the nanofiber, then the spin for symmetry reasons also has to flip. And that means that here the role between left and right detector for circularly polarized light changes, and the light comes out at the other end of the fiber if I put the gold nanoparticle below the fiber. If I convert the measured photon fluxes or directionalities into an asymmetry of photon fluxes, then the directionality of 0.88 here corresponds to an imbalance of 16:1 photon flux coming out of the two ends of the fiber. For this measurement here, we even have an imbalance of 40:1. And it turns out that there is no limit, even theoretically, to that. So once we analyze the data, we noticed, but then the experiment was already disassembled, that you can go up to arbitrarily high values. So basically no light coming out of one side of the fiber. So this was now an experiment that was purely classical. So as I said, the gold nanoparticle can just be considered as a small antenna for light that emits light dipolar radiation of a polarization that we can choose by just tuning the incident the polarization of the incident light field. Would of course be interesting now to realize a quantum version of this experiment. So, and actually we did such an experiment by coupling cesium atoms to the waveguide. So for reasons of time, I cannot go into the details how exactly we do it, but take my word for it that by using additional light fields in the nanofiber, we can actually trap using the dipole force, so a two-color dipole trap, cesium atoms in a one-dimensional potential array of trapping minima at a distance of 200 nanometers from the nanofiber surface at a well-defined azimuthal position. Okay? And now we illuminate these cesium atoms from the side with a resonant light field. So if you look at it like that, you would say this is exactly the same experiment as the one you did with the gold nanoparticle. But there's an important difference between the gold nanoparticle and the cesium atoms, because the gold nanoparticle is a polarization maintaining scatterer. It's a spherical particle which will replicate the polarization of the incident light field. A cesium atom, however, is a multi-level atom, and the polarization of its emitted light is governed by dipole selection rules. So depending on which of the excited states of so actually we drive the cesium atom on the D2 line, the upper state has a total spin of 5, the ground state a total spin of 4, and depending on which of the Zeeman sublevels of the excited state we drive, we populate with the laser field, we have different polarizations coming out of the atom. So for this outermost Zeeman state here, the atom can only, due to dipole selection rules, emit a sigma plus polarized photon and decay to this lower level here. So in this case, you would expect a strong directionality because the photon is circularly polarized. The same is true for the other opposite Zeeman substate, where the atom can only emit a sigma minus polarized light field, and that should then exit, this photon should exit the other side of our waveguide. If, however, I populate more inner-lying Zeeman substates of MF equals +1 or -1, then the dipole selection rules allow for sigma plus, sigma minus, and pi polarized emission. And sigma plus will come out one side of the fiber, sigma minus on the other side of the fiber, and pi will be evenly split. So here you expect a much smaller directionality. So if I now plot again the same quantity as before for the gold nanoparticle, so this directionality, however, this time as a function of the magnetic quantum number of the excited state, then this is what we observe. So here, directionality versus magnetic quantum number. So the red bars are the theoretical prediction taking into account dipole selection rules and thus the polarization of the emitted light. And the dots here are experimental. And you see that for the outermost Zeeman substate here, we indeed have a very strong directionality. The imbalance of photon fluxes for this measurement was 10:1, whereas the imbalance here is much, much smaller because we have all three polarizations radiated by the atom. And I would like to stress that this now is a quantum state controlled directional spontaneous emission in the sense that you encode the direction in which the photon is emitted into the waveguide via the magnetic quantum number of the excited state. So I would also like to stress that this kind of directional spontaneous emission is not exclusively observed in our experimental system. It will occur or can occur every time that you have a spin momentum coupled light field, and the spin momentum coupling occurs every time that the light field is transversely confined so that the amplitude has a strong gradient in the transverse direction. To my knowledge, the first time that such a directional spontaneous emission has been observed was in South Korea in 2012, where they looked at surface plasmon polaritons. So this here, the screen is a gold film, okay? And they have a slot in the gold film and illuminate the slot with a laser which is circularly polarized, and they see that the surface plasmon polaritons go rather to one side than the other here of this slot, okay? The first time that such an experiment has been observed with what I would call photons, so in dielectric waveguides, was in the group of Mark Fox and Maurice Skolnick. where they had a cross of two linear dielectric waveguides, and they had a quantum dot in the center here, and then they excited the quantum dot and looked at the power that was outcoupled out of these 4 ports here. And this is actually a nice story, because this experiment was never designed to see directional spontaneous emission. What they really wanted is to be able to analyze the polarization state of the quantum dot, okay, which can be either sigma plus or sigma minus or linear, by measuring by doing an interferometric measurement of the phases of the 2 light fields that come out here, okay? And then the PhD student came to see Mark Fox and said, look, here's the data, I have more light coming out than here. And he said, go back to the lab, this is wrong, you know, do the measurement again, do it properly. And the poor student had to do it several times until they found out that that was not a bug, but actually physics that they were observing. The same for us, so we actually observed this directional emission when studying the coupling of a single rubidium atom to a whispering gallium mode resonator, and we saw a spectrum that qualitatively disagreed with the theoretical predictions that were using a theory that was used for 25 years for describing interaction of atoms with whispering gallium mode resonators. Gerd Leux and Peter Banzer looked at the scattering of a gold nanoparticle on a dielectric interface. They illuminated it with a radially polarized, strongly focused beam so that they could also have circular polarization in a plane that is normal to the interface. And they saw that the scattering into the substrate was not like conically symmetric, but that the light rather went to one than the other direction. And in the group of Peter Lodahl, as well as Kobus Kuipers and Ruud Olten, they studied the emission of quantum dots of emitters in photonic crystal waveguides. Actually, out of all these experiments, the only ones that were using quantum emitters is the one here by Peter Lodahl using quantum dots, and our experiment with rubidium atoms and with the nanofibers coupled to cesium atoms coupled to nanofibers. So with this, let me just check. Good. I come to some useful application of all this directional coupling, which is actually realizing non-reciprocal nanophotonic devices where the light transmission is different from the left and from the right. So maybe first a few general words about non-reciprocal devices. So maybe the most well-known non-reciprocal device is a Faraday isolator, which is based on the so-called Faraday rotation. So Faraday rotation is an effect which occurs in magneto-optical materials or also in alkali vapor cells, has been demonstrated by Charles Adams and Durham, for example. And it occurs when you apply a magnetic field along the direction of propagation of the light field. In this case, in a magneto-optical material, if you send a linearly polarized light field into this crystal, then the plane of linear polarization will turn, and the sense of turning this polarization is determined by the sense of the B field. Okay, so that means that I have a plane of polarization that is different at the exit of my material here than at the input. And the angle beta by which the plane of polarization is turned depends on the length of the crystal. It depends on the strength of the magnetic field. So it's proportional to both the length of the crystal and the strength of the magnetic field. And the proportionality constant is the so-called Verdet constant, where this constant is a material property of the magneto-optical material. Okay? So using this Faraday rotation, you can realize an optical isolator by putting this magneto-optical material between two polarization filters, which are turned by 45 degrees with respect to each other. Because in this case, if I send light into port 1, it will go through this first polarization filter, and it will exit, because here this polarization filter is turned such that the light exits with unity transmission through this filter here. So unity transmission meaning that this just transmits. If I send the light backwards, however, then the polarization plane will turn in the same direction and will end up being orthogonal to the incident polarization, meaning that this filter here will just block the light. So this realizes a optical isolate, and optical isolators are very important optical elements in the context of telecommunication and laser physics, because they prevent light being back reflected into your laser or other components which might be sensitive to back reflection and possibly even be damaged. By using polarization beam splitters rather than just polarization filters, I can also realize, using Faraday rotation, a so-called optical circulator, a 4-port optical circulator, because in this case the light that is sent back into port 2 here will be reflected by my beam splitter and come out of port 3. And if I send light into port 3, it reflects from the beam splitter and then is reflected on this beam splitter, comes out of port 4. If I send light into port 4, it's reflected here. Here it is just transmitted, comes out of port 1. So I have a transmission which goes port 1 to 2, 2 to 3, 3 to 4, 4 to 1. This is the principle of a 4-port circulator, which is important, for example, for wavelength multiplexing. You can add signals on one waveguide, etc. So it's also a very important component. And now if you look at, so for this to work, what you need is this angle beta to be 45 degrees. But this means that if I have a given B field strength, I need a given Verdet constant that depends on the length of the crystal. The typical length of crystal for these bulk optical isolators is on the order of a centimeter. And if I have a centimeter long crystal and I have a magnetic field strength of 1 Tesla, which can be realized just by putting permanent magnets close to the crystal, okay, I actually need a Verdet constant which is 80 radians per Tesla and meter. And this is readily available for high transparency materials, so you can just buy these optical isolators in the Thorlabs catalog. However, if you now want to miniaturize such an isolator, say make the crystal shorter, okay, for example 100 times shorter, then I mean typically I will not be able to get a much larger magnetic field. I'm limited by the field strength of permanent magnets, which will be on the order of a Tesla. But then the only way to make an isolator would be to crank up the Verdet constant and make it 8,000 rather than 80 radians per Tesla and meter. Now, actually for certain wavelength ranges, you just don't have a material that has such a high Verdet constant. So no way of realizing at all an isolator which is miniaturized, say for 850 nanometers for cesium wavelength. And for other wavelengths, you may have such a high Verdet constant. However, the high Verdet constant comes at the expense of a high loss as well. So actually, the shorter the isolator, the higher the losses, because the Verdet constant also comes with a high absorption of the material. So this shows you that realizing non-reciprocal integrated optical devices is really a non-trivial task. There are ways around it. But actually, I should maybe first say a few words about integrated photonics in general. So if you like, everything has been demonstrated by now in integrated photonics, light sources, detectors, amplifiers, you name it, it's there. However, for this reason of high Verdet constant, but also because the typical surface waveguides are birefringent, the Faraday effect that we use in the bulk optical isolator cannot be used in this case here, because I can, even if I had a material that has the high Verdet constant, I cannot smoothly turn the polarization in a rich waveguide on a substrate, because this waveguide is birefringent and has two non-degenerate polarization modes. So that means that even after 40 years of research, non-reciprocal integrated optical devices are not commercially available, and the ones that have been demonstrated so far, so here are examples how you can do it, they actually so far failed to combine high isolation with high forward loss. So how was it done here? This is like a Mach-10 interferometer where you put magneto-optical material on top, which couples to the evanescent field that sticks out of the waveguide. Here it's a whispering a ring resonator with a magneto-optical film on top. Interestingly, in both cases, what they do is they apply a magnetic field that is orthogonal to the direction of propagation. And we will understand how these isolators work. So the idea is now that you actually make use of the spin momentum coupling of light. Okay, so we remember if we send linearly polarized light into the waveguide, I have counterclockwise light if I send it from the left. I have counterclockwise polarized light above the waveguide. If I send it from the right, I have clockwise polarized light. So what I need now in order to realize an isolator would be scatterers that couple to this light field, which couple differently to clockwise and counterclockwise light. And it turns out that, for example, cesium atoms that are spin polarized do this job. If you spin polarized cesium atoms, meaning that you prepare them in the outermost Zeeman ground state with maximum projection of the spin, then the transition for sigma plus polarized light can be resonant with this transition. But if I now apply a magnetic field which is normal to the direction of propagation, such that this transition, this polarization drives this transition, and this polarization drives this transition, then I can tune, using the Zeeman effect, I can tune this transition out of resonance. So if I now send light into the fiber, from one side it will couple strongly on this transition, the atoms will scatter it out of the waveguide. If I send the light from the other side, then this light will not be resonant with the atom, not coupled to them, the light just goes through. Interestingly, however, you do not even need the magnetic field to be applied. So even if I now turn off the magnetic field such that this level shifts into resonance with the counter-propagating light field, it turns out that the transition strength of this transition is 50 times larger in cesium than this transition strength. So this transition strength is given by the Clebsch-Gordan coefficients 3J and 6J symbols. And it turns out that the ratio here is so high that I even realize an isolator with cesium atoms that are just spin polarized without external magnetic field applied. Okay? So you might ask, how is that possible? Because in typical non-reciprocal devices, I mean, you need something that breaks time reversal symmetry. Because if I run the movie backwards, the light goes backwards. So I should have something that breaks the time reversal symmetry in order to realize a non-reciprocal device. And it turns out that in this case, it's the spin of the atom itself which breaks time reversal symmetry. Because if you look at a spin polarized atom and you run the movie backwards, then it will be in this state. Okay? So it's the time reversal transformation properties of the spin that break the time reversal symmetry. And when doing this experiment, we indeed observed a strong difference between forward and backward transmission, that the forward transmission was 78%, whereas the backwards transmission was only 13%. This corresponds to an isolation of 8 dB, and the job was done by 27 atoms. Now you might say, I'm not impressed by 8 dBs because I can buy a Torlabs isolator which has 30 or 60 dB isolation, but it turns out that at the time when we did this experiment, this high forward transmission in conjunction with the high isolation was world record for integrated optics. Okay? So if you take as figure of merit the dB of the isolation per dB of forward loss, then this was the best that was ever realized. Now, another comment here, while this optical isolator is based on a quantum optical effect, right, it is still a classical component. Because if you wanted to prepare this diode here in a quantum superposition of passing light from the left and passing light from the right, you would have to prepare all 27 atoms in this state, quantum superposed with all 27 atoms in this state. So this would be a giant Greenberger-Horn-Zeilinger state, which in the lab is not practical to realize. If you wanted true quantum functionality, then it would be much better if we had the job done by a single atom, because that can be easily prepared in a quantum superposition of states. However, in our experiment with the nanofiber, the coupling strength per atom to the waveguide is only such that we have about 4 to 5% absorption per atom. So while you could realize a non-reciprocal transmission, it would be a lousy isolator. But there's actually a way to realize enhanced coupling of a single atom to the resonator by mediating the coupling to the nanofiber via a whispering gallery mode resonator. Okay, so here the atom is now not directly coupled to the waveguide, but the atom is coupled to a so-called whispering gallery mode resonator. This is a cylindrically symmetric dielectric structure where light goes around and is guided by total internal reflection. And then I can tune the coupling strength of the atom to the waveguide by tuning the distance between the nanofiber and the whispering gallery mode resonator. Okay? I should stress that here we have rubidium-85 rather than cesium. So here the ground state spin is 3 rather than 4. But still, if I now prepare the atom in the outermost Zeeman substate, I can single out here such a V-level system where when the light is sent from the left through the nanofiber, it couples into the whispering gallery mode resonator and circulates counterclockwise. And now the important property of the whispering gallery mode resonator in this context is that it will preserve also the spin momentum coupling, because again I have an evanescent field which has a strong transverse intensity gradient. So if the light circulates counterclockwise in the whispering gallery mode resonator, the E field will turn clockwise and drive this strong cycling transition in the atom. So if I probe the system by sending light from here and tuning this light field, okay, then the empty resonator will show up as a dip of transmission. So here I plot the transmission through this fiber as a function of the tuning of this laser light field. And let's first look at the gray line. So this is just the empty resonator. And you see that I have a dip here, which is the resonance of this resonator, which goes to basically 0 transmission. So this can be set by tuning the gap here to the right distance such that I'm critically coupled. So then you can see this resonator as a kind of impedance matched absorber that just dissipates all the light in the fiber. And if I now couple the atom to the resonator, then I see that the coupled system atom plus resonator actually gives rise to this double peak structure. So is the so-called vacuum Rabi splitting. The atom couples strongly to the whispering gallery mode and splits the resonance into 2 new eigenmodes, and I see that the transmission goes up at resonance here. If I now probe the same system, okay, atom plus whispering gallery mode resonator, from the other side, however, then the light field will circulate clockwise in the resonator, the electric field will turn counterclockwise and drive this transition here. And in this case, the imbalance, again, due to the different transition strength, here it's not 1 to 50, but 1 to 30 roundabout. But this means that this transition is so weak that the atom does not influence the cavity mode. It's basically not there. So you see both with and without atom a single resonance here, which goes down to basically 0 transmission. Now this is a very non-reciprocal system. We're probing one and the same optical system, sending light from the left and to the right, and have 2 very different transmission spectra. In particular, that allows us to realize an optical isolator if you now consider the on-resonance transmission. If I send light from the left, then the atom is strongly coupled to the whispering gallery mode resonator. It prevents the light from entering the resonator. The light just exits, and I have high transmission. If I send the light from the right, then the atom is basically not coupled to the clockwise mode. The light just enters the resonator, is dissipated therein. I have low transmission. Okay? And this realizes now an optical diode. The isolation was even higher than for the ensemble case. So we had 13 dB of isolation, and this job was done by a single atom while still having a high forward transmission. Okay? So here we control the propagation direction with a single atom. However, this is still not a quantum device. Because while it's possible, of course, now to prepare the atom in a superposition of spin states, the device is based on losses, meaning that the first photon that I send into this isolator would either go through the fiber or be scattered into free space, and I would know and thus project the spin state of the atom, and all consecutive photons would not be treated the same way. But there's a way around that. What we need to do is we need to get rid of this dissipation. So we don't want the light field to be scattered out of the resonator. It should stay in my circuit. And that is possible by actually using a second coupling fiber here, which is at the same time coupled to the same mode of the whispering gallery mode resonator. So in that case, with the atom, I still have this diode, so transmission in this direction because the atom is strongly coupled. If I send light into port 2, the light goes into the resonator, is weakly coupled, but now, rather than being dissipated in the resonator and scattered into free space, I couple it out more quickly, and I just send it into port 3 here, okay? And if I send light into port 3, light goes counterclockwise, is strongly coupled, so it cannot go in. If I send light into port 4, the light goes clockwise, is weakly coupled, goes in, comes out of port 1. So this means it goes 1 to 2 to 3 to 4 to 1, and this is the principle of operation of an optical circulator. And actually the scheme was proposed by the group of Jason Twomley at Macquarie University, and we just realized that. So the parameters you can tune now is the coupling strength of these fibers here to the resonator by tuning the gap between the resonator and the fibers. I don't want to go into all the details here, but rather just say, look, we have transmission as a function of coupling strength, and there is a sweet spot. So let's concentrate on these data points here. So you see that indeed for this 1 to 2 diode, I have high transmission, low backward transmission, okay? For the 3 to 4 diode, I have high forward transmission, low backward transmission, and also for the 2 to 3 and 4 to 1 diodes, high forward and backward transmission. If I transform or calculate the isolation from these transmission values, then they are actually for all 4 diodes 5 dB up to 11 dB here, and the photon survival probability still was pretty high. It's higher than 70%, meaning you send a photon into this circuit here and it comes out with 70% probability. And what I cannot show you for time reasons is that actually by now flipping the spin of the atom, I can reverse the operation direction of the circulator. So rather than routing 1 to 2, 2 to 3, 3 to 4, and 4 to 1, it would route 1 to 4, 4 to 2, 3 to 2, 2 to 1. So we have a spin-controlled routing of light. So actually, by just flipping the spin of the atom, we have a kind of roundabout for light that switches from continental Europe to Hong Kong, okay? And you just send the light one way around or the other. So yes, that's good. Maybe one last point I should make about this circulator is about the nonlinear properties, because so far what I described was only the linear response of this non-reciprocal element. However, it will of course react differently if 2 photons arrive at the same time, because the atom is a 2-level system. It can only scatter 1 photon at a time. So naively speaking, and the theorists, please excuse me for using just the CAT1 and CAT2 for 1 photon and 2 photons, I will say what we really measure. What I described was the linear response, so meaning that here if we send 1 photon and there is an atom in the resonator, then the photon cannot couple into the resonator and comes out of port 2. But if 2 photons arrive simultaneously, then they actually saturate the atom, so the photons can enter the resonator and exit port 4. Okay? And now what did we really measure? We send in a weak coherent light field, so just the laser, resonant weak laser light field, and we measured the intensity autocorrelation function at this port and at this port. Okay? And then indeed you see that at port 1 we have an anti-bunched signal here, because we are the probability for 2 photons making it through the fiber is reduced by the fact that they go into the resonator. So anti-bunching on port 1, whereas on port 4 here we have a strong bunching, because the 2 photon component is kind of filtered away from this light field here and scattered into this port 4. Okay. So with this, I would like to summarize. I presented the guided modes in optical nanofibers and their strange polarization properties to you, and I showed you that the local polarization is linked to the propagation direction of light and the fiber, and I showed you that you can make use of this so-called spin momentum locking of light to realize a directional emission of light into the waveguide, both in the classical and quantum regime, and then I showed you that you can also realize non-reciprocal nanophotonic elements which make use of spin-orbit coupling of light. And just because here are people that work with microwaves as well, I should stress that actually you can see these elements as quantum optical analogs of microwave ferrite resonance isolators. So it's exactly the same spin momentum or locking of light or of microwaves takes place in rectangular waveguide, microwave waveguides. And the engineers, of course, knew that for decades and just put a in that case, radio magneto-optical material and a strong magnetic field, and this is how these isolators work in the microwave domain. So where can all this lead to? I showed you that we did some rudimentary optical signal processing and routing of light in an integrated environment, and I told you that this is not so easy when it comes to non-reciprocal elements. I should also stress that these devices are compatible with single photons because some non-reciprocal elements are based on non-linearities, but then they only work for high powers, okay? Whereas here this works in the linear regime down to the single photon level. One other thing I would like to stress is that all this shows us that we might want to revisit the so-called one-dimensional atom model. So the one-dimensional atom model is a term that was coined by Jeff Kimball, as far as I know, which refers to the simplest possible model of light-matter interaction, a single two-level emitter coupled to one propagating field mode, which either propagates backwards or forwards. And because all the predictions, and I would even say dogmas, that are known about the one-dimensional atom model are actually based on the assumption of symmetric coupling to the forward and backward mode, whereas it's indeed possible to have a fully chiral coupling to such a pair of modes and thereby get qualitatively new effects. Okay? For example, sub and super radiance, which are also based on this coupling to a single field mode, are also based on symmetric coupling to the counter-propagating directions. And so there's, for example, an absence of sub and super radiance in the chiral coupling regime in the sense that sub and super radiance don't exist like we know them for the symmetric case. So the nonlinearity that I showed you is of the Kerr type, and one might say that this is not useful. There are papers saying that Kerr nonlinearities don't help quantum computation. I would object because there is a nice paper that shows that using such a Kerr nonlinearity, you can build an error-proof Bell state analyzer, and you can also build quantum non-demolition detectors for photons and other things. So I still think that this Kerr nonlinearity is useful. And finally, by considering the collective coupling of a number of two-level emitters to a single mode which exhibits spin momentum locking such that you have chiral coupling, you can actually realize a very strange dipole-dipole interaction, because in free space, two dipolar emitters will always interact symmetrically, meaning that one acts on the other like the second one on the first. However, here, there is no back action because this emitter can absorb light coming from the left, but then it can only emit to the right. So this emitter here never knows whether there is one here because there's no information backflow, and that gives rise to novel phenomena in quantum many-body physics, and maybe it's also interesting for quantum simulation. And if you find all this interesting, then you might have a look at the review that we wrote together with the groups of Peter Lodal and Peter Zoller that appeared in Nature recently. And with this, I would like to thank my co-workers that did the experiments. I would like to thank the funding agencies, and I would like to thank you for your attention.
Thank you very much, Arno, for these exciting new elements and insight into polarization optics. Questions? There's one over there.
What is the process by which a gold nanoparticle re-emit light? Is it some sort of quantum mechanical process, or is it some more like classical diffraction?
So it is actually a plasmonic resonance. So it's a collective It's a collective excitation of the free electrons. You can see it as if you had a free electron gas that is actually bound to the core, to the ionic core of this plasmonic particle, and then it's just a harmonic oscillator. You can see it as a Lorentz oscillator, a charged harmonic oscillator. And it has an eigenfrequency which you can choose by choosing the size, and in our case, the size was 90 nanometers, giving rise to a plasmonic resonance at 530 nanometers, so green light.
Further questions?
So it's sort of a naive question, but in your first example where you send light in perpendicular to the direction of the fiber, I'm wondering about momentum conservation. So how do you?
Well, so momentum conservation in the dipolar emission is not conserved neither, right? I mean, you send light onto a dipolar scatterer and it goes isotropically into free space and you get radiation pressure. And so here it's the same thing. Part of the emission goes into the waveguide, and of course the atom will feel a force, but the atom is trapped in a dipole trap in our case, and so the dipole trap takes the momentum. Actually, the dipole trap is, I didn't explain in detail how the dipole trapping works, but it's a three-dimensional trapping where all 3 dimensions are better localized than the wavelength, and we are in the Lambda-Dicke regime for all 3 dimensions. So in that sense, the answer to an Eintrapper would be the Eintrap takes the momentum.
Okay, I see.
Further questions?
Thank you. So is it possible that with the chiral waveguide, we can construct quantum gates between single photon and single atom? Thank you.
So the answer is yes. There's a work by Barak Dayan at the Weizmann Institute where they use these whispering gallery mode resonators coupled to waveguides. And actually, in order to realize a quantum gate, however, you need more than, if you want a quantum gate between photon and atom, you need a qubit, but you cannot use the excited state of the atom as 1 qubit state because it decays in 30 nanoseconds. So what you need is you take 2 hyperfine states of the atom, which are coupled via a Raman transition. And then the exciting thing is that actually a single photon, in this case, will, with unity probability, trigger a Raman transition between the 2 hyperfine ground states. So once the atom is excited, cannot decay back to the same channel, but will go to the other state. So I can actually send a photon, the hyperfine state is flipped, and the photon is reflected. Okay? And this is a true quantum gate, because now sending the photon from left and in a superposition of sending it from left and right actually entangles the path of the photon with the internal state of the atom. And that has been demonstrated. So as always, it was marginally quantum. I can't quote the numbers, but it was good enough to say that it's a quantum process. Yeah.
More questions? Christophe.
You mentioned that it was difficult technically to make the atom into a superposition state of the +5 and -5. But this morning we've seen with Jean-Michel that you could prepare any superposition of M states.
You heard something that I should have said, but I didn't say that. What I said,
Exactly.
what I said was that it's difficult to prepare a GHZ state of 27 atoms in the superposition of these 2 states. And I swept under the rug that even with a single atom, it is still challenging to prepare a superposition of the 2 outermost Zeeman ground states. But as we saw this morning, and there's also work by Paul Jessen, for example,
Yes.
it is possible. So it is challenging, but you can do. Paul Jessen does a full ground state manipulation of the 16 ground states of cesium and claims that he can prepare any superposition state of these levels.
So in your case, this would be then a coherent superposition of counterpropagating. There would be Bell state or
So what you would realize,
ideally.
actually what you would realize in this case, let's go here. if the atom is in a superposition of the two spin states, then for one spin state, the light field goes through. For the other spin state, the light field goes to port 4. So you entangle path and internal state, but interestingly, this is now a quantum device in the sense that if I have a long, a very weak but long coherent pulse, such that the probability for having two photons at the same time at my scatterer or at the resonator is very small, then to a good approximation what you will prepare is a Schrödinger cat, because the weak laser pulse will then go through here if the atom is in one spin state, and it will be routed to this port if the atom is in the other spin state. Okay, so as I said, for that you need the pulse to be sufficiently narrow band to interact resonantly with the atom resonator system and to be sufficiently faint such that you don't have two photons arriving at the same time, because otherwise this nonlinearity that I showed would kick in.
So just a comment. This device would be a kind of quantum beam splitter.
Yes.
Because in a classical beam splitter, the photon pass is made into superposition, but the beam splitter does not keep any information. Here, the beam splitter keeps the information of the pass.
Exactly.
So you could play a lot of complementarity games with this kind of device.
Yes, correct. So, but I should stress that for doing this, we would need to be able to prepare and analyze the quantum superposition, and for that we need the atom to be there for long enough. And in the experiment I was showing here, while for the nanofiber ensemble we trap the atoms, for the whispering gallery mode experiments it is still free-falling atoms, and the interaction time of the atom with the resonator is only a microsecond, and unfortunately this will not be enough. So right now we are working on very boring things, but very challenging, which is trapping an atom in the evanescent field of this whispering gallery mode resonator. Actually, that was the initial topic of my PhD.
Okay, now the circle is almost closed. Are we ready? Thank you very much, Arno.